Triangular numbers. Going back in history more than 2000 years, Pythagoras and the Pythagoreans were interested in establishing relations between geometric figures and numbers. If you take 1, 1 and 2, 1, 2 and 3 stones and arrange them in a particular way, you may be able to produce triangular figures. This is now believed to be the origin of the triangular numbers, the square numbers, and other figurative numbers. Triangular numbers are obtained when we arrange a number of stones in an equilateral triangular shape. As we can see in the figure, we have the first 3 triangular numbers, 1, 3, and 6. The first triangular number is 1. The second triangular number is 3. To obtain 3, we need to add 1 and 2. To get the third triangular number, we add 1 plus 2 plus 3. Can you guess now the next triangular number? Yes. You guessed right. The next triangular number is 10. 10 is the result of adding 1 plus 2 plus 3 plus 4. So there is an intimate relationship between triangular numbers and the sum of consecutive natural numbers. If we call t sub n the nth triangular number, then we can define the nth triangular number to be the number obtained when we add the natural numbers 1, 2, 3 until n. From our definition of triangular numbers, we can see a direct link between triangular numbers and the sum of the first n consecutive natural numbers. It would be nice to find a shortcut that would allow us to compute easily the sum of the natural numbers 1 plus 2 plus 3 until n. A problem similar to this was solved a long time ago by a very young child. He became later in life one of the greatest mathematicians in history. His name was Carl Friedrich Gauss. The story goes that his teacher Butner wanted the students busy working on additions for a while. So he asked the students to compute a lengthy sum, and for that, he chose the numbers in a way that he could easily verify the answers himself, without having to do the full computation. To his astonishment, one of the students finished the addition with the correct answer in a very short time. Obviously, that student could not have possibly added the 100 numbers in such a short time. That student had to have had a very simple and bright idea that allowed him to easily solve the problem. The teacher immediately understood how bright this student was, and from that moment forward paid special attention to develop that student's talent. If you had not seen this problem before, now you had the opportunity to solve the same problem that Gauss solved when he was young. Stop the lecture and try finding the sum of the first 100 natural numbers. That is, find the value of 1 plus 2 plus 3 plus up to 100. If you have tried for 15 or 30 minutes and you do not come up with an answer, then come back here and see how Gauss solved the problem. Gauss solution. Gauss realized that when you add pairs of numbers from the beginning and the end of the sequence, like in 1 plus 100 equal 101, 2 plus 99 equal 101, and 3 plus 98 equal 101, the sum remains constant. It's easy to see why this happened. That is because one number, the first one, is increased by 1, while the second number is decreased by 1, so the actual sum stayed constant. What the young Gauss discovered was an invariant. An invariant is some property that does not change value. You may now think, why is this helpful? Well, it seems now that we have translated the problem of finding a sum of 100 different numbers to a problem of finding the sum of 50 equal numbers. Can you guess why 50? That last problem is very simple. The answer is 50 times 101. So the answer to our problem is 5050.